Dear all, myself and Professor Ted de Jong would like to welcome you in the second episode of Hort Forum, sponsored by ICHS. We will discuss today the present and the future of the use of autonomous equipment and robotic harvesters in field-based fruit production. The goal of this event is to engage you in a frank discussion of the potential use of autonomous machines and harvesters in orchard and other fruit crops. We will begin with a summary talk by Stavros Vougioukas, followed by panel discussion that will be coordinated by Professor de Jong. We will try to be provocative to keep the audience engaged, and after the panel has a chance to initially discuss the issues, we will try to take questions from the audience via the chat application. Thanks again for attending this episode, and I hope you to enjoy the interaction today. We have the pleasure to have today as official speaker, Professor Stavros Vougioukas. Stavros is professor in the Department of Biological and Agricultural Engineering at the University of California at Davis. Before joining the University of California, he worked as a postdoctoral researcher at the Department of Industrial Engineering at the University of Parma in Italy, and as a faculty at Aristotle University of Thessaloniki in Greece. He's currently leading several research projects on robotic harvesting and labor-saving technologies, and on precision yield mapping with funding from USDA, grower commodity boards, and the industry. Stavros, the floor is yours.
Thank you very much. I hope everybody can hear me and can see the slides. Thank you very much, Ted and Georgios, for the introduction and for the invitation, of course, to present. I'm really delighted to address this audience. The title of the presentation is indeed the present and future of the use of autonomous equipment and robotic harvesters in field-based fruit production. I will focus on robotic harvesting. And yes, field production, I'm not going to discuss at all any issues in greenhouse automation, although some of the principles I will describe apply to that too. So it's probably not news to this audience, but I like to have this slide because it's shocking for many people. Pretty much all of our fresh market crops, fruits, vegetables, berries are hand harvested. Every single one of those fruits has been picked by a farm worker. And this is where we are now. But when I show these slides, people then ask, what about harvesting robots? We read in the news, podcasts, we see on the web a lot of information and news about fantastic, great new harvesting robots that can harvest apples and kiwis and strawberries and other fruits. So when we have these, why do we still need to use people? Well, this webinar would like to address the following issues. First of all, explain why harvesting with robots is difficult, where we are now, or how we can improve the situation. The second part will discuss harvest aids, which is a technology related, or it is a robotic technology, but it's an intermediate step, if you will, to complete automation. And then part three will take a bird's eye view and look at regulation, labor, and production systems, and how the interplay of those with robotics is. So let me proceed with part one. And in order to understand the limitations and the capabilities of today's robots, it would be nice to understand the fruit harvesting steps. If you are a human or a machine, if you're somebody who is trying to pick fruits, well, the first thing is these fruits are either laid out on trees in orchards, or they're on strawberry or other cane bushes. And so you need to position yourself, to position your hand close to the fruits. The next phase, once your hand is close to the fruits, is for you to actually find where the fruits are and use your hand, in this case, if you're a human, to pick them. And you keep doing that until you fill some personal container, maybe a plastic box, a clamshell in the case of strawberries, or a picking bag that you are carrying if you're on a ladder picking apples, for example. Once that container is full, you need to transport it to a collection station or to a bin, empty it, and then go back and reposition yourself to the next tree or the next bush and repeat this process over and over again for several hours, usually under the hot sun. So the most difficult of these tasks seems and actually is the center one, the picking. And so agricultural harvesting robots have focused a lot in this area. And to say the truth, robotic harvesting is not really a new idea. It's been around for many decades. The feasibility of using a camera and an arm and software to pick was demonstrated even from the 70s. On the left, it's a black and white picture of a harvesting robot. This is in a lab, it's not in the field. The publication is 1977. And at the right is another robot picking citrus. Actually, one of our faculty members, Professor Slaughter, this was his PhD thesis back in Florida, 1989. So the question is, how come, we had those robots back, 40 years ago? Where are today's robots? How do they look like? Well, these are some pictures. They definitely are in color and they look much better. And we can see examples of robots that harvest kiwis and strawberries and apples. And so the question is, okay, we have these robots. Are they actually picking? Are they being deployed in the fields? And the answer, or the short answer, is most of these robotic harvesters, if not all of them, are still prototypes. Some more mature, some less mature. And the reason is that building a cost-effective harvesting robot is very difficult. Building a robot to just pick fruit is relatively easy nowadays. It can be a thesis of a master's student. But building a cost-effective one is not easy. And the reason for that is harvest cost is defined by three main factors. And I'm citing a paper from the 1980s, but it's still relevant to a large extent. And those three factors are the purchase price of the machine, the fruit picking efficiency. This term refers to if I have 100 marketable fruits on the tree, how many of those fruits can the robot pick and safely put into the bin where they will be transported? And so picking efficiency is that component, that factor. And then pick cycle time is another factor. How many seconds does it take to pick a single fruit, or how many fruits per second you're picking? So the efficiency and the speed are extremely important in this business. And so let's talk about them to understand what the current limitations are, where we are now, and where we need to get. So let's tackle picking efficiency first. Picking efficiency, as I said, is the percentage of marketable fruits you can get from the tree to the bin. So that process has a few stages, right? So first of all, a percentage of the fruits on the tree are visible. Not all of them are because of occlusion by leaves and other branches or fruits. And then out of that percentage, another percentage can be perceived by your amazing machine learning system, your computer vision system, right? And then out of those fruits that you already detected and localized, only a certain percentage can be reached by your mechanical arms and grippers. And then a percentage of those that are reachable will actually be successfully detached from the tree. And then a percentage of those fruits that are now in your robotic gripper will be conveyed to the bin, to the final destination. And the problem with efficiency, as we all know, is that if it consists of multiple factors in series, as we see them now, the overall efficiency is the product of the partial efficiencies. And that can be a big problem, because if one of those efficiencies is low, the entire efficiency goes down. Here's an example where you multiply 95%, which is a pretty good number. And if you multiply it 5 times, you get 77%, which means that 23% of the fruit does not make it to the bin. That's not a very good number. Now, where are we now? Very few companies, probably almost none, will publish such data. But I'm citing a paper here from the scientific literature. This is an amazing and excellent kiwi harvesting robot in New Zealand. This is a 2020 publication. And take a look at these numbers. 93% of the kiwis were visible. And this is a relatively nice situation where the kiwis are hanging. 98% of those are perceived. So they have a great computer vision system with AI and you name it. But unfortunately, only 43% of those fruits were reachable by the arms and the grippers because of obstruction and occlusion. Out of the reachable ones, 95% were detached, 92% were conveyed. So technology was working great, but the overall efficiency was 34%. This is not a number that qualifies this robot to go into an orchard and harvest commercially, although the technology is excellent. What can be done to improve the picking efficiency? Well, first of all, we need to address each of those links of the chain. And we also need to be pragmatic and realize that engineering alone is not going to make it. We also need a systems approach that includes breeding and horticulture. And that's why I have the green and the black fonts there. So visibility is a huge problem. In some orchards, you may only see 60, 50% of the fruits with a camera or a set of cameras. So if you could use breeding and horticulture to make a simpler and thinner canopies, decrease the foliage or have less fruit clustering, that could raise visibility. On the other hand, you can use multiple cameras. You could use active view, so moving the cameras around to get a better view of the fruits, or you could even do canopy actuation. For example, one strawberry harvester actually pushes the foliage in a way that it exposes the fruits. People have tried also blowing air in the foliage of apple trees in order to expose the fruits better. So you can see how there are ways to go about that. Perception is a lot about better algorithms and more training data these days. Reachability, again, can be facilitated by simpler, smaller, and thinner canopies, but also better machine design, mechanical design, and controls. Detachment has to do with clustering. So if you have less fruit clustering, you're going to be more successful. But also it has to do with how well designed your gripper is and whether it's controlled well enough to not squeeze the fruit, etc. And finally, fruit conveyance has to do with the resistance of fruit to damage. So if that's increased, that's better. Also, it has to do with arm design and machine design. So I hope now everybody realizes that efficiency is a major factor and it's an important challenge for us to increase. But that's not the only challenge. Let's talk about the peak cycle time. We need to be fast. We can't afford to spend 1 minute to harvest one fruit. And the peak cycle time comprises several components. One is you need the machine to position itself in front of the current tree or region of the canopy it's harvesting. You also need some time for perception to find the fruits. You need some time to actually mechanically reach them using your arm. You need some time to detach them with your gripper, and you need some time to transport the fruit from where the gripper is in the canopy to where the gripper can actually deposit it in some conveyance system. And again, the problem here is that all of those times must be added to each other. So how well do humans do? Well, we've measured strawberry pickers, and it takes them about 2 to 4 seconds to pick a berry on average. That's not counting the time it takes to transport the tray to the edge of the field. If we are talking apple harvesting, if a person is on a platform and they're harvesting apples, at least according to our measurements, they take anywhere from 1.5 to 2.5 seconds to harvest one fruit and put it into their bags. So these are the numbers we are competing against. And of course, most companies will not publish numbers, but this is again data that these researchers were kind and brave enough to publish. And the kiwi harvesting robot with its 4 arms working together achieved anywhere from 2.8 to 3.2 seconds per fruit. So even if it was using 4 arms, the speed was similar to a human picker. I'm not sure how fast kiwis are being harvested, but I believe they're harvested at this speed or maybe faster per person, per one person. So what can be done to increase this speed or reduce the peak cycle? Again, systems approaches are paramount. So for example, if you have denser plant spacing and smaller canopies, it takes less time to position the robot to the next picking position. But again, if you have better machine design and controls, you can do something about that. Perception, faster hardware and software, interleaving perception and action will help in terms of time, of course. Reachability, the time it takes to reach a fruit has to do with how simple and thin the canopies are. If you need to control your arm around branches and obstacles, it's more expensive, but it's also slower. We need better design of machines, better algorithms and controls. For detachment, again, fruit clustering is extremely important. And then gripper design and controls are again important for speed. And finally, transport, that's extremely important because you need to design your system very well so that the fruits that are picked and they're in the gripper of the arm don't delay too much until they're transported to the container, to the bin, for example. So hopefully by now we understand that the challenges with robotic harvesting are not that we can't do it. The challenges are that we cannot, in most cases, do it fast enough and efficiently enough to justify the cost. Let's look at harvest aid robots. So let's revisit the previous slide where we showed the different steps of harvesting. Robotic harvesting focuses on picking, which is the center part. Well, harvest aids target the positioning and the transportation components. They make it faster and easier for people to position themselves close to the fruits and also to transport whatever they have harvested. And so they increase efficiency and safety. It's not a new idea, by the way. These are pictures from a platform on the left. It's definitely not robotic. It's from the 50s, and it has a crew of 8 people harvesting in an orchard. And then on the right, you see essentially what is a long conveyor belt that's moving slowly in front of the pickers so that they don't need to go back and forth from the edge of the field to deliver their harvested crop. So an old idea, what's the state of the art? Well, it has changed a lot. On the left, you see a platform, an orchard platform. This hasn't really changed drastically, although there is more automation. It can steer on its own. And in the center, you see a platform where there is a vacuum transportation or conveyance system. So the pickers don't need to unload their bags into a bin. They simply put the fruit that they harvest into those receptacles, and then the tubes carry the apples into the bin. On the right, you see some very nice, interesting robots from 2 different companies that are used to carry table grapes. So instead of people moving back and forth and carrying the grapes on wheelbarrows, these robots can be trained to actually follow people around or to move back and forth inside certain rows and carry the produce for them, thus saving them time. So this looks really cool, and we can get significant savings by deploying this technology in the order of 30 to 40% for platforms, and for transport aids, the gains can be higher, although we don't know exactly based on advertisements, but I will show some numbers next. So the question is, if this is the state of the art, what are the challenges? And I will claim that there is a lot of space for the robotic harvest aids to increase even more the efficiency and safety of the crews by providing adaptive, individualized service. What you see in front of you are advanced machines, but they essentially are picker agnostic. They do some operation, but they don't really collaborate closely with the pickers in an optimal manner. So let me show two case studies from our own research that moves in that direction and are relatively close to being commercialized. We'll take the example of strawberry harvesting. So this is how people harvest strawberries in California. They fill up a 5-kilogram tray, and then they rush out to the end of the field to a collection station to deliver, get credit for it, get an empty tray and go back. And they're not supposed to run because of safety issues, but they do because they're paid piece rate. Now, we have measured that they spent anywhere from 10 to 25% of their working time just moving trays around, running back and forth. And so our idea was, what if we change that and replace that task with robots? Well, was it a new idea? No, there are machines out there that will help people not deliver trays. This is an example of what's called the Mercado machine. It serves 7 to 9 people, and it's a tray transport service system. So essentially, instead of you going back and forth, that huge machine travels in front of you at a slow pace, and you put your tray onto that machine, and you work in a group of 7 to 9 people. There are smaller versions by other companies for anywhere from 2 to 4 people. So these machines can provide some efficiency improvements, some benefits, but they're also problematic in some ways. I mean, the big machine, of course, is expensive. It's difficult to turn. But the other challenge here is that people are different and they have different harvesting speeds, but also the amount of crop they have in front of them varies because the yield is not uniform. So here is a figure that shows you how much it takes for one person to pick a 5-kilogram tray of strawberries in a California field. This is a frequency histogram that tells you that time varies anywhere from 100 seconds, which is about 1.5 minutes, to 500 seconds, which is more than 9 minutes. It's very wide. And so that means that the demand, if you will, for transport service by the machine per picker varies a lot. But the supply of transport service by the machine, if you have a large machine, is the same. It does not really match this varying demand. The result is, if you have 8 people walking behind a large harvest aid, some of them are far behind, some of them are close to the machine, and some are tempted to even go faster than the machine. So you are constrained by the slower picker in a sense. Anytime you have such imbalances, you have inefficiencies. And so perhaps the solution would be to have one robot per picker. That would be fantastic. Of course, it doesn't work because that would be too expensive. So here is a project, here's an idea where the concept is to use a small number of robots that are intelligent so that they can monitor, if you will, the pickers. They can predict when and where they will need a tray transport service and offer it to them. This was a project funded by NIFA under the National Robotics Initiative. And here you see in fast forward speed the operation of two of those robots. Basically, they go out to pickers somewhere there, but they know when and where to go. And then the picker simply puts their tray on the robot does the transportation. Also, it provides empty trays to the pickers. And so problem solved. So this system, of course, looks pretty boring, which is great. That's what we want technology to be like. But it was very difficult to develop. This is what happens when the robot is in front of the picker. The picker doesn't need any training. They just deliver their tray on the robot, push a button, the robot goes away. So it's supposed to be easy. How does it work? The pickers work on, they use little carritos, little strawberry picking cards that are like $40 each to hold their trays. Well, we actually instrumented these cards with a GPS, a scale to measure the weight of the strawberries. We send all of this data in real time to a computer, and then the computer does some cool scheduling and some smart assignments so that it assigns robots to pickers when the pickers need the robots. On the side, it also generates yield maps for strawberries, which is a manually harvested crop. So this is something that never existed in the past. Now, how well did they do? Running commercial field experiments in commercial fields in California in low yield season, November, and using 2 robots for 7 workers, we managed to get efficiency increases of about 12%. And these will be higher when we have a high yield situation. So that's one example where robots offer individualized service to pickers, and these robots can actually serve multiple pickers. I would call it the next generation of robotic harvest aids for berries and cherry tomatoes and table grapes and crops like these. A second example I will show later is for apples, but people ask, did the workers like this system? And the answer is they did, or that's what they told us when we ran the experiments. But in general, for them to accept those machines, they need to see clear benefits, and they want flexibility and control. They don't want to feel that the robots are mandating some things. They want to feel that they are their servants. And so the benefits are actually clear because the robots guarantee the picker that they will harvest more trays because they save walking time. And so that may mean more money for them. Also, they reduce walking and sleep accidents. So it increases safety, it reduces fatigue for the pickers. And by the way, they offer a lot of flexibility because they are robotic systems, they can be programmed. So a worker can actually pause and resume robot service if they don't like the robot for some reason or they don't want it. And the robots can provide individualized service because they monitor the picking rate of the picker, where they are, how fast they move. And the word monitor is meant in a good way. And so if the picker has been working for a long time, let's say 20 minutes without rest, the robot may not go to them or may stop far away from them so that it forces them to walk, or it may offer specialized service to specific pickers, etc. Moving on to the next case study, this is apple harvesting, classical ladders, bags. Of course, we nowadays have commercial orchard platforms where people stand on the platform to pick. Those increase efficiency and safety a lot. But the trouble with them is that they assign pickers to pick from different heights that are fixed. And by that, essentially, they create harvesting zones for each picker. So one picker harvests at the top, another picker may harvest at the bottom of the row. And the problem is that fruit load may be different in different heights, and picker speed may be different too. So you can imagine a situation where the top picker is slower, but they have more fruit in front of them, and the bottom picker is faster, but they don't have much fruit. Again, there is an imbalance between supply of labor and demand for labor. So our idea here was to robotize these platforms, have a camera that creates a map of where the fruits are, and then having a computer actually control the elevation of the pickers while it's measuring its harvest, the harvest speed of each person, and thus provide an optimized performance for the entire machine. So this was, again, another robotics project funded by NIFA. The goal was to build a better harvest aid platform. And you can see the sketch here, the diagram. You have two people on this platform on one side. You have a camera. The people can be lifted by hydraulic lifts. And the 3D camera finds all the fruits in front of them. It builds a fruit map in real time, of course. And then the computer controls the lifts so that it matches picker speeds to fruit load, but also it provides an adaptive speed control or cruise control. So it changes the speed of the platform, again, in a way to optimize performance. This is a picture from the platform we built and tested in orchards in Lodi, in California. And we did experiments in 2019 with Fuji trees in a wheat trellised orchard. Two pickers were harvesting, and we tried either the conventional mode where the pickers were picking manually at fixed heights, and one of the pickers was controlling the speed of the platform. And then we tried the full core robotic mode where the computer was doing everything. And we harvested, 1.4 and 1.9 tons of fruit. And we also tried harvesting while clipping the stems or not clipping the stems. This is a short video of the machine. I will lower the volume here. And I will fast forward, but you can see how the picker in the front, the lift is moving up. And then the picker in the right, again, the lift is moving and everything is controlled by the computer. The pickers just harvest. Results, let us focus on the highlighted numbers. When we were clipping stems, we had an 11% increase in performance, in total speed of kilograms picked per hour. And then when they were not clipping, we actually had a 26% increase in total speed versus manual. So you can see again that we have improvements of anywhere from 10 to 25% when we introduce robotics into the harvest aid technology. Okay, so part 3, which is the concluding part, let's talk a little bit about ag robots and regulation, labor, and production systems. So, are self-driving robots legal for agricultural practices? Well, in California, the short answer is no. So there is a Cal OSHA regulation that says that any self-propelled equipment, when it's moving under its own power and it's in motion, it must have an operator stationed at the vehicular controls. So that means that even if you have the most amazing spraying or harvesting or pruning or whatever robot you have, right now, if you want to be legal, you have to have a person on riding the robot or next to it so that that person has full control. That person is the operator, if you will, of the robot. Now, there is strong push from industry to change the regulation, and it will change because of all the technology and the progress, but there are still some issues. The bigger issue is the lack of safety standards. Such standards are under development at the international level right now, but it will take some time. And so the lack of standards is a major cause behind of the lack of regulatory and legal frameworks. In other countries or continents of the world, things are vague. So Again, overall, we still need some work for ag robots to be legally deployed. That doesn't mean that they are not used, but they are used on private property. And typically there is an operator from the company that built the robot who is or who are supervising the process. What about robots and non-trained farm labor? And the term non-trained, I was actually, I used to use the term unskilled, but I was informed, and it's very true, that farm labor is not really unskilled. They're very highly skilled and they're very smart and capable, but they haven't been trained to do other things. So when they're non-trained and we just want them to pick, well, the fact is that we have fewer and fewer of farm workers available. And that is not only true for US and Europe and Australia, it's the same in China, in Asia, Latin America, even in Africa. Demographics, urbanization, other issues are creating this effect. Now, we need to understand that in harvesting, the existing technology may reduce the need for unskilled, excuse my use of the term here, labor, but it will not eliminate it. And the reason is that robots are not perfect. They will always leave behind a percentage of the fruit unharvested. That might be 20%, it might be 70%, we really don't know, it really depends. And that means that we have human crews that must clean up after the robots. And the challenge there is to incentivize those crews. Because if you're a picker, a farm worker, and they call you to a field where the low-hanging fruit, if you will, has been picked by a robot, and you have to find the more difficult to pick fruits, that will be slower. You're not going to pick as many. So you need to make money. So either you will not go to pick on that farm, or you have to get paid more. So there is an issue there. And the economists, of course, are very aware of that and are analyzing this effect. But it's not only economics, it's also social components there. The other thing is that the production systems may change. For example, in strawberries and grapes, the robots may pick in the field, but not necessarily do the packing. One specific strawberry harvesting company has a robot that puts the strawberries in larger boxes because it's very complicated and time-consuming to pack them in the field for them. And then they introduce a packing line for strawberries, which is unheard of. But maybe that's a better equilibrium point for the system than what we have today. Maybe not. But again, that needs to be explored. What about ag robots and trained farm labor? Well, like I said, we will need machinery operators or supervisors for these robots. We don't have them. Machinery operators are not available, and they're becoming more and more scarce. And these autonomous machines will need people who have higher skill sets, and those people need also to have some knowledge of farm operations. So that combination will also need to be paid more of skills. So, we may take away some low-paid jobs, but then we will introduce some fewer higher-paid jobs. So that also needs to be figured out. Business models. Nowadays, all of those highly specialized ag robots, these are actually prototypes by companies. They're offered on a service model. So and actually some of the harvest aid robots, they are rented. And so that is great because in the future, that technology may be accessible to small growers because they don't need to invest a lot of money to buy a very expensive machine. Also, they don't need to have the people in the farm to maintain or configure these machines, etc. However, general purpose autonomous tractors and some expensive harvesting robots for almost all year long crops like strawberries will be offered using an ownership model. And so questions again are there related to maintenance, intellectual property, data ownership, liability if something goes wrong with these machines, etc. So I would like to conclude here. I hope I'm not over time, but some of the take-home messages are that harvesting robots work well only when the fruits are easier to find, reach, and detach. And then we can improve that. We can improve the performance of robots through breeding, horticultural practices, and engineering, but it will take some time. It's not happening tomorrow. I will not give numbers because that's very challenging, but it's not happening tomorrow or next year. Harvest assist robots, on the other hand, have been already shown to increase efficiency and safety for people. In the near future, they could provide even more individualized service to the workers, so more performance increases and safety and convenience. They can also gather valuable labor and crop-related data that we don't have, so we can improve the management of the labor, but also of the crop itself. And the great thing is it's doable now. We can do it now. We are doing it now. Of course, the limitation is that you cannot improve efficiency by 100%. It's going to be 10 to 20 to 25%, maybe a little bit more depending on the task. And finally, production systems, when you introduce robots, may change. I believe they will change because now you remove some of the assumptions and constraints of having people picking and possibly packing in the field. That can liberate you to think out of the box. We will need fewer non-trained and more highly trained farm workers. And then we will probably utilize a blend of ownership and service and rental models, which is actually a great opportunity for smaller farmers to utilize this technology. And by these take-home messages, I would like to conclude my talk. Special thanks to my ex-students and postdocs, Chen and Cheng Hao, for working on a lot of the technology that I showed. Denis Sadowski, who built everything in our lab, anything mechanical, he does. And then growers and anonymous farm workers for helping us conduct our experiments. Thank you very much. I will be very happy to discuss with the panel and take any questions.
Okay, thank you very much, Stavros. We will now go into the discussion part, and for the panelists, we have Lorenzo Marconi. He's from Italy, and he's specializes in autonomous vehicles, autonomous systems, and he's not necessarily spent that much time in agriculture, but he's is a computer autonomy expert. And we have Inez Hanran, who is with Washington State Apple Commission, and she's also an apple grower. And she's had a lot of involvement in the development of robotic harvesters or funding of those projects and so forth in Washington. And we also have Tim Delbridge, who's who's at Oregon State, and he's an ag economist who's done some economic analysis of robotic harvesters and automated harvesting. So with that, why don't we start off with Lorenzo, and if you have a few comments related to Stavros's talk and also comments of your own.
So thanks a lot, Ted. Thanks to everyone. And very nice and inspiring talk by Stavros. And yes, I come from Bologna in Italy. I'm a professor at the School of Engineering. And my main expertise are in automation, automatic control. And just recently, I entered the field of agriculture, trying to bring some algorithms and technology and expertise that we developed in other fields in agriculture, trying to cross-fertilize the field. Also working a lot in collaboration with the School of Agriculture here at the University of Bologna. And so the talk was very, very inspiring. Recently, we founded a spin-off company, and the idea was trying to invent the new robotic technology in agriculture, the new tractor, let's say, and addressing also picking and robotic task in agriculture in several fields of agriculture, not only orchards. And so I found that the talk very, very inspiring. And my first consideration is that probably integration is the key issue right now in addressing the big challenge that harvesters, robots pose in agriculture. So if you take all the technology and sector and topics that Stavros presented, each of those has a state of maturity that is huge. So if you pick perception algorithms, actually you can really perceive everything. If you pick robotic grippers, the development that have been done in recent years is incredibly high. And if you pick mobility and positioning, again, you have many algorithms and many solutions that are really incredibly high. So in the product of efficiency that Stavros showed before, each of those parts are very high. And to me, the big issue is integration of all those. And integration are the cost-effective solution. So you can really obtain some solution that is reliable, robust, and cost-effective if you're able to integrate all existing technologies that by their own are very, again, with a high maturity in the perfect way. So integration to me is the challenge. And you have to integrate mechanical components, electronic components, artificial intelligence components. So very high mature technologies that should be integrated in a very effective way. So to me, the big challenge is over there.
All right, thank you, Lorenzo. And as you've had a lot of experience watching and looking at robotic harvesting experiments and machinery.
Yeah, absolutely. Yeah, so I'm placed here in the northwest, very northwest of the United States. This is where most of the apples in the US are produced, in Washington State. And we have been basically trying to mechanize, just like Stavros said, since the 60s, since the late 60s, early 70s, try and come up with a picking machine. And you can see that this hasn't been very successful yet. I would say what we think, with the current machines, what I think some of the biggest challenges are not actually the picking. Maybe you could argue the picking speed, because eventually a machine has to, and this is now something that is actually that you can argue about, but it has to eventually replace pickers, or it has to be as good as at least more than one picker, otherwise you don't really gain anything. And this is also where some of the problems lie, because I just said it, replace picker. And this is what usually the media picks up right away. That's where they always want to go. We have a real big problem talking about this to the media or to the general public in general, so that nobody goes there, oh, we're taking a job away. As an example, we have had over 30,000 jobs in agriculture unfilled last year, and they were openings, and only 11 people applied, and all of them were hired, and the rest were not, but they were open. But this is a story that nobody wants to talk, and it's really hard for us to get the public to go behind this. And also for us, a problem just talking about it. Stavros did a good job, and you didn't say once replace people, which is great. But basically, the status of all the machines that we've looked at is right now, they're as good as 1/2 picker. Well, that's not really. So you have a $400,000 machine and you're not actually gaining anything, you're going backwards. That's not really good. But I think one of the bigger problems in terms of having the technology eventually ready to be in the field is actually more on the transfer side. Because I think picking speed, now that we have grippers that can pick things, that can be increased. This is like just now a technical problem, but then having the fruit being transferred fast enough into some sort of a container, I think this is an area that most companies, if not all, underestimate to date. That is a much bigger problem, because right now at a slow speed everything goes, but at a faster speed it's a big problem. And so I think this is something that people need to focus on. I would say I really agree with Stavros on the genetics portion and on the growing systems portion. We've done a lot of work here in this area already on growing thinner canopies and having varieties that are lending themselves better to being picked. For example, we have some varieties like Cosmic Crisp that they self-thin themselves, so they naturally set singles, which also eliminates one of the other big things that you have to do, or big cost factors, and that is hand thinning of fruit. And so if you have varieties that do this naturally already, then you have an advantage there in the system. And we've been focusing on our breeding programs on having fruit that is less sensitive to bruising, which is of course a big problem because you have this mechanical damage when you put in picking machines. One of the problems we're now actually encountering is, in order to be really efficient, most of our growers are growing fruit in this V-trellis structure. This makes you hang more fruit per acre, but a lot of the machines that we are testing right now, they don't work very well in these V-trellis systems. So one of the challenges will be, how can you utilize these systems that are clearly more efficient in producing most fruit per acre, but how can you merge this with the machinery? I think there is another thing that we think will help us increase the pick cycle. And that is, I think a lot of the machines are right now, they're like going there, picking, going back and dropping. There is some new concepts that go there, pick and drop right away. That way you can really increase the cycling. I think those are some of the concepts that are really, that I really like. And one of the things that we learned here in our area is you have to work with the growers. So that's really important, both for companies and scientists. At the outset, basically work with the growers, so you don't design something that will never work. And I really liked how Stavros actually worked with not just the owners, but also with the pickers themselves, because we had the same situation. The folks didn't tell us the truth, what they didn't like about things. So we had to really be smart about trying to figure this out. And lastly, I would say financing is a big problem. Basically, the developmental cycle takes about $50 to $100 million. We had an example here of a company that already failed because of that. So a lot of times, the investors that invest in this kind of technology, they're looking at this from an industrial point of view, and that is, you have a return on your investment after 3 to 5 years. And in these, especially in perennial cropping systems, this is too short of a cycle. And this is where that needs to be adjusted in terms of when somebody invests, they need to know that after 3 to 5 years, you do not have 50,000 orders of a machine in. And this is why most of the time, basically, companies do really well all the way to that, and then they go into the death valley and they cannot come back out and ultimately have sales of machines. And that's an area that we're really trying to focus on, to try and help companies bridge that divide and get there. And that's something where we need international collaboration, because this is too big for one commodity, for example, to solve. So we have done something that's called the Global Harvest Automation Initiative, that is centered at the Western Growers Association, California, where we're trying to focus on the 20 top crops, and try and basically by working together on a worldwide basis, trying to help push this entire sector forward.
Okay, thank you very much, Ines. So, Tim?
Yeah, thank you. And Stavros, wonderful talk. I agree with so much in there, and I was pleased to hear a lot of the topics that am hoping to hit were brought up in your discussion. So a couple of things. One, I really appreciate the simplicity of your framing of the excuse me, harvest costs is really dependent on these three main factors of picking efficiency and speed, and then the price excuse me, of the equipment. There's one piece that doesn't directly impact the cost, but certainly impacts the feasibility, and that's the wage rate, right? We're comparing human labors to the technology. You know, we're going to see if wage rates continue to increase, as we expect that they will, as new regulation comes into play and the labor supply continues to shrink as the demographers expect it to. And that threshold of adoption, how good the machines have to be before they're adopted is going to fall a little bit, right? We don't know exactly how much. There's a lot of numbers in play here, but that's something to keep an eye on for sure. The other thing regarding the wages that I think is relevant is that I don't know that it has to come out exactly equal or better for the robots before we'll see producers start to lean on these systems. You know, actually the H2A program in the United States is an interesting case here, right? In that I know we have an international audience, but the H2A program, where we're able to bring in workers from other countries on temporary work visas, it's quite costly for growers to participate in this program. There's a lot of bureaucracy. They have to supply housing. They have to pay wages that are above the local wages. In many ways, that's more costly than paying local wages because of the housing requirement and all of the bureaucracy required. But you still see huge growth in the program. And when you talk to growers, candidly, they'll say, well, sure, it might cost a little bit more, but there's more certainty, right? We know that we're going to have labor available if we bring these H2A workers in. They're less like, well, they can't go to the farm across the street because they're on our visa. There's a bit more stability. And I think the robotic solutions provide that stability, right? And so I do think that we'll see growers pay a little bit for that reduction in uncertainty. And again, you know, the numbers always get tricky, and this is the situation where the devil's in the details, but conceptually, I think that that's an interesting thing to think about. The other thing I wanted to just highlight, I really appreciated the focus on this concept, right, of imbalance equals inefficiency. And my background, I'm at Oregon State now, but most of my work in this area has been on strawberries when I was previously based in California. This imbalance equals efficiency concept is also seen in the strawberry harvesters, right? We've got a range of different competing machines, but some of them quite large. Maybe they're 4 beds across. We have 16 picker arms. And if you have one plant and one picker arm is assigned to that plant, if that plant has 7 berries on it and the plant next to it has 0 berries on it, the machine might pause, wait for all 7 berries to be picked off one plant before we move forward. And so again, this concept of a systems approach, and we have to look at integration. You know, we might see a scenario, you can imagine a scenario where it's actually optimal for the berry to be abandoned so that the machine can move forward. If I'm no geneticist, I don't know even what's feasible, but if you could get more balance biologically on those plants, you could see increases in efficiency. So this applies in a lot of different areas, and I like that. And then finally, the I assume we'll get questions about, or maybe for the next round of discussion, we can talk about farm size and consolidation implications. I think that that's really important. And one area that's, kind of central to that is the use of data. I love your focus on, you mentioned the yield map that could be produced, not from the robotic harvester, but from the harvest aid, the burrow or the one of the other competing pieces of equipment, where you can actually develop a data set of yield density across the field spatially. And I think it's an exciting topic that needs further attention, right? What do we do? How can we most effectively utilize all of the data that you can achieve by taking 1,000 pictures of every plant in the field twice a week, right? Once you can wrangle that and use it for scouting purposes or yield prediction purposes, I think we're going to see a lot of benefit. So anyway, yeah, I think I generally agree with your conclusions about timeline and adoption, and there's still a lot that we don't know.
Okay, thank you very much, Tim. So I just started going through the questions. And I also would like to address a bit of the what effect could this potentially have on further consolidation of farms, and will the small farmer really be able to handle it if you have even some of these harvest aids that are potentially expensive. I know in our case in California, we have a lot of mechanical harvesting of nut crops and also prunes. And while those machines are not super expensive, but there are a lot of service companies that do them, that provide that service. But growers still have problems. The small growers still have problems getting the service of those companies when a large grower comes along and says, I want to, I need your services. The service companies tend to serve the larger growers first. And so we still have, the service model doesn't necessarily solve a lot of these problems. But anyway, so a question from Craig Campbell. Could you imagine a time when two types of produce are sold, conventional and hand-picked? Wait, somebody just at a premium. So will there be, so the question is, will this have an effect on actual marketing so that people would like organic fruit, hand-picked fruit versus machine-picked fruit? Anybody thought about that?
Well, some of the European strawberry harvesters in the UK, I believe they market berries with the stem on. And I've heard some robotic harvest developers argue that that's the fruit that should be sold at a premium, because you can pick the fruit from the stem without ever getting your dirty hands on the berry, without bruising the berry, and it actually ends up with a higher quality berry. But it's an interesting concept. I wonder, with the genetic developments that might make the fruit more robust and durable for robotic harvest, we might see more differentiation on the cultivars that are bred for flavor instead of durability, which might have a kind of an overlap with the robotic harvest.
Yeah, I got some comments on that too. So, I mean, we've seen it with eggs, right? You have the normal eggs and then the free range eggs and then the chickens that are really happy. I don't know, all kinds of different differentiation. So I can see that, although in general for produce that doesn't bear very well, because just pitting organic versus conventional usually already causes a lot of confusion on the consumer side and usually leads to consumers eating less fruit. So that's something from a marketing point of view to really think about very carefully. One of the areas that I think is where more research is needed and where we can have the help of physiologists is really understanding abscission as it relates to maturation. We have this problem, for example, with cherries. The cherries usually have the abscission layer at the end of the stem and not between the cherry and the stem. If you want to harvest them mechanically or realistically, it would be much better to have a cherry without a stem because it would keep a lot longer because the stem sucks the moisture out of the cherry. But also people are, of course, used to stems. So there's a lot of layers in that system where we need more answers. And the same is true for any of the fruit that needs to upsize. For us to regulate the abscission so we can manipulate it, that it comes off at the time when we need it and at the right area where we need it, that would be really super helpful.
Okay. So we have a question about the robustness of these machineries and concern about breakdown and those sorts of things. Do we really think that this is that they're these highly technical machines? What's the breakdown prospects and will the growers have to have on hand technical people to do that?
Yeah.
Go
ahead, Lorenzo.
Yes, so I believe that, of course, there is a big revolution in terms of maintenance and assistance to those machines. Everything goes to the electric, fully electric. There is maybe in the future no anymore hydraulic stuff. Will be no endothermic engines. So there is a big revolution that is the same revolution that automotive is experiencing now. And probably this revolution will touch also this agriculture sector soon. So in terms of robustness, I believe that the technologies that are expected to be used, to be integrated in the application context we are dealing with are by their own robust. So they are off-the-shelf commercial product that have been tested and experienced in other industrial or application context. So by their own, the technology is robust. To me, what is still missing in the agriculture is the fact that everything is picked from other sector and reused in agriculture. Most of the picture that in solution, at least most of them that Stavros have shown in his presentations is based on robots that maybe are general purpose robots. I saw universal robots, anthropomorphic solution. So they are used in many other sectors. They are not specifically designed for agriculture. And this is probably a problem in terms of robustness because they have not been conceived specifically for the harsh environment where they are expected to operate. And also this is impacting the cost and in the efficiency, in the speed, and all the points that Stavros touched in his talk. So to me, again, what is missing is to use the technologies that by their own are really robust, because again, we are not talking about the disruptive new technologies, something that are exist since ever or since many years, but they should be properly integrated and properly used in that specific sector. And what Ian said before, actually, since the numbers are not huge, international collaboration is a key, because we have to really work as a team at the international level to have not single small actions, but a big action that is seen and conceived at international level.
So yeah, this is a good question. We ran into this a lot because most of the pieces, they have ratings in terms of durability and what they can do, but when you actually take them out to a field, usually those ratings don't hold up. And especially when you have dust in the system or heat, it just doesn't work very well. So that's been a big. Those are small issues, but they become big issues. But what we have been talking with the folks that we're working with is that we need a very easy interfaces. So most of the machines we've been working with have a really easy dashboard system with like an on and off buttons, very little buttons. So everybody could theoretically run the machine. And then the other thing that can be done, and that's been done here on a lot of our machines, is that you have somebody from somewhere else can troubleshoot the problem. So it's not so much that that you take the machine apart in the field when something happens, but that you have somebody that sits somewhere else that can actually detect the problem and potentially even fix the problem remotely. But what we feel has been really important is some trusted local, let's just say, supplier that people already know, and that there is some technical backup and some local production. I would also say one of the other things that some people like to think that electric vehicles are the way to go. We don't think so. I think it's much better, or we think it's much better to have hybrid motors. That's a lot better, even though electric right now is very popular. But from an agriculture point of view, I don't think that makes a lot of sense. And then of course, growers like to still dabble with things themselves. So we are working with some solutions where we have easy click and play systems where you can change, for example, end effectors yourself to still have that touchy-feely system that people are used to. And that basically, we haven't mentioned that yet, a lot of this machinery will work a lot better if it's multifunctional, if it doesn't just pick, if it also prunes, and if it thins, and if it does other things. Yeah, I think that those are some additional points that haven't been raised yet.
Thank you, Inez. So I have a question. So people have been talking about multifunctional machines for a long time, but are there any examples where that's actually come to fruition in terms of a harvester that's then used for a pruner? I know we have mechanical pruning systems and so on for grapes and other things, but as far as I know, people talk about multifunctional, but it's not so well developed.
Yes, it's true. Most of this is at the research stage right now. So there's a lot of funded research projects going on at the moment, but nothing that somebody can take, a grower could take off the shelf. You're absolutely right.
I also, what about how big a problem is it if your field is not level and you're working on slopes?
Yeah, good point. That is a very big problem. A lot of the machinery does not work very well on slopes. And that's going to be a big problem in a lot of growing areas. Not everybody's like California.
That if I may add, regarding multifunctional machines, Inez is correct. There is some research going on now. The idea is if you have a machine with multiple arms, by changing end effectors, maybe you can pollinate, maybe you can cut, you can thin, etc. So it's a great concept, but we also need to understand it's very difficult to add multifunctionality. In what sense? If you optimize a system to do a certain task, you can really optimize it to be very efficient. As you open up the different tasks it does, it may become non-optimal for the main task. Let me give you an example. If you want to pick fruits, you may want a very light arm that can move fast, right? Lightweight arm. But if you want to really prune and having a heavier cutting tool, maybe that arm needs to be also heavier to carry that load and apply all the forces, etc. And that may mean that that arm is slower to harvest. So it's a difficult challenge, but of course it makes a lot of sense having a machine that you can use, 8 months in the year rather than 2 months in the year. And as for flat terrain, yes, everything that's been done is for flat terrain right now. Undulating and hilly terrains are very challenging. In terms of the machine, it's going to be more expensive, probably heavier. So we are trying to address the main problems of, let's harvest, let's prune, let's thin, and then tackle the problems. Let's do that now on a hill.
Yeah, and I would say even regarding harvest, what we found is that for each variety, you have to basically change your code a little bit and do it a little bit differently. In some cases, it's better to do like some sort of a twisting motion, and in some cases, it's better to pluck it. And there's going to be differences of what would work best for efficiency for each variety. And then with pruning, I think a lot of the efforts so far have been, in our opinion, a little bit thinking too broadly. I think pruning would be easier if it would be just focused on one thing, one type of cut, like one type of renewal cut, and do that, and then move on and do a second kind of cut instead of trying to do everything at once. I think, yeah, and I know folks are working on this, but it's just been a really much slower process than we imagined. We haven't really mentioned yet that one aspect that we haven't really utilized, and that might actually be something that does increase worker efficiency, is using VR systems. VR systems to basically show somebody where to pick or where to prune in a more efficient way. And that is something that a lot of the young people really like, and that would actually maybe even bring young people more into doing this, because that's what they're doing anyway in their spare time. And it could really help to do things efficiently and not have to think so much. And that would be like the skilled versus unskilled labor, even though we don't want to really say it like this, but this could really potentially help us out. And that would be, I think, a really interesting area for folks to work in.
Okay, so I have a question about fruit maturity and selective picking. So the machines that are out there today, are they differentiating what fruit is mature and what is not? I mean, in the apples or in the strawberries, or in the stone fruit, we have a big problem because stone fruit we typically go over 3 or 4 times. Looking at picking more mature first and so on. Do we envision, or are any of the current systems handling that, or is that something down the road?
Well, I can say about that. If maturity correlates very well with color, or if we depend on size, then cameras and machine learning systems are very good at doing that. So for example, strawberry harvesting, the cameras and the vision system needs to differentiate between red, green, red, green, and in general peak based on maturity. Size is also possible, but if it has to do with, I don't know, pairs and pressure, or if it has to do with composition and sugar content and things like that, then unless you have some way to sense that fast, then it's very difficult to do.
And then when if it's possible to differentiate by color, let's say the simplest case, I have a question about the economics of running that machine through the orchard 3 or 4 times.
Inez,
to
I
give-
don't know, maybe he said
Yeah.
economics, so maybe he's
Yeah,
looking
this
at
is
me, but I
not
think we should look at you.
economical.
Yeah.
What we're typically thinking is the first most economical step is to pick the outside of the tree and the tops, and that usually has also the fruit that matures the first, and that's easy accessible. But also the tops, taking away some of the ladder work and then having maybe a ground crew come and do the second pick. What we really think is, of course, a better way is to really focus on the breeding and having varieties that mature evenly on the tree. So you don't have that question about maturity. You have everything mature evenly. And at the same time, though, you need to have a broad harvest window, because if you have something that rolls within one day, that doesn't give you a lot of flexibility. You need something that holds steady for 2 or 3 weeks on the tree so you can get to it. And so that's been the focus for us to do this. Yeah, and then of course another focus area is more focus on non-destructive sensing, so that eventually we can sense, based on other parameters. Yeah, sugar or firmness, especially for pears. This is very important to have some additional measurements. Otherwise, you can't harvest pears effectively.
Okay. I'm going through some of the questions here. Most people enjoyed your presentations and the discussion. I have some questions about, there's one question about whether the next step is to build the orchard to fit the robots, and I think that's already been answered. We definitely would have to do that, I think. But then you have what was brought up in the first Hort forum, and whether there's a yield penalty cost for doing that. The question about how does the panel see autonomous harvest machines integrating with additional ag techs and other farming operations. I think that we discussed that a little bit with pruning and various things, but it's not really well developed yet.
One thing I could add here is that once you have robotic harvesters or harvest aids, you get tons of data related to the fruits themselves, but also to the crop. Of course, you get data when harvesting takes place. And so, for strawberries, for example, harvesting takes place twice a week in California. So you get a lot of data from crops that didn't have any data at all. Again, strawberries, for example. So linking that data to AI, machine learning models, improving some type of management, etc. I see a lot of linkages there. So those machines are also data gatherers, and there is an obvious linkage there.
And I'll say that holds for farm management, but then also for marketing purposes, right? In berries in particular, it's incredibly valuable to be able, excuse me, again, incredibly valuable to be able to forecast with some accuracy what your yields will be 2 weeks later. So you can deal with your retailers and schedule promotions and those sorts of things. And right now, it's difficult to do, and the accuracy with which they can do it is really dependent on human scouts and the machine learning models. They've been looking at prediction models just for maybe 2-week yield forecasts, but there's not much improvement from the machine learning models because that human input is so valuable. And so if that piece of the scouting puzzle, of the prediction puzzle, can be replaced or supplemented by in-field robotic data collection, I think that would be a value that's often understated.
Can I add, Ted, about this multifunction question? So I'm a big fan of multifunctionality, but probably must be properly framed. So I totally agree with Stavros that the implement should be super specialized. So if you design a robotic arm for harvesting, probably it's not the same robotic arm for pruning. And if you design something for spraying, probably you have to design that specifically for that operation and cannot be reused for other things. Otherwise, the efficiency and all what Stavros touched in his presentation is affected. On the other hand, what you can do is to design, for instance, some common locomotion system. This is how we are in Bologna, we are pushing a lot of design attention. So the locomotion system, the tractor is the same. So actually the farmer can reuse it in several tasks and several operations all over the year. What you change is the specific implement on it, like the PTO. So it's actually the same principle, but a little bit revised and in terms of new robotic solution. And this also probably change the way in which the business model is brought to the field. So the service versus the ownership model. So if you're able to design something that can be really reused or in different operations, probably is a technology that can be very, very effective and interesting for small farmers and not only for huge ones. So everything is correlated, the business model and the solution we are able to develop. And multifunctionality properly interpreted is a big issue.
All right, yeah, thank you. That makes sense to me. I mean, yeah, because these machines are going to be quite expensive, and so a grower needs to be able to use them in as many things and amortize that cost against many functions. So I had a question for Stavros maybe and others. So we have these, you had the very nice example of the strawberry conveyance system. And there were also the grape conveyance systems that you show. Those are fairly modest advances, but still really quite significant, I would say. So are these being adopted, and are there companies taking up the technology and marketing it yet, or what's the deal?
Right. So the two pictures I showed are from robots that are actually out there. One company is selling them. The other company is either selling or renting. Actually, I happen to see a $4,000 per month price tag on one of those transport robots for table grapes. And I know that there are other companies that are developing similar systems or more advanced systems. And so the answer is they are now available commercially. I believe there will be more of them. And now I don't know the extent, like how many units are being sold or how many units are being rented, etc. But it's growing, at least in the table grape industry. I haven't seen anything for strawberries yet on the commercial side. But my feeling is that we'll see more and more. There is a lot of interest, not only from these crops. I've seen interest from the coffee industry in Latin America, for example. They are facing huge labor challenges, and so I see adoption being going up very fast for these types of systems because they have been shown to work. They're relatively simple to deploy, don't need much training, and you get savings immediately from day one.
So what's the major limitation to adoption? Is it getting the technology from the researchers to the company, or from the company to the growers?
Well, I think it takes time. So if somebody is deploying robots and they're seeing gains in efficiency, that's one grower or maybe a company, but we are talking about thousands and thousands of acres, right? And so it takes time, first of all, for the news to spread and for people to get convinced that they want to deploy them. But I would suspect also that if demand increased very, very much, some of those companies would not be able to meet that demand because there are still startups, there are smaller companies. So that could become an issue. But those would be my, my main points.
Yeah. So the
Yes.
large machinery companies are still not getting into this.
The large companies are more into autonomous tractors. So, for example, we have seen John Deere invest in that space and have a product. CNH has invested in other startup companies for autonomous tractors. So they are very much into that space. We've also seen John Deere work closely with GAS, which is a company building a orchard sprayer. So we start seeing some involvement when there is a ripe product that's, that shows promise, then big companies will actually come over and take over the company and incorporate the technology. But we haven't seen that yet for the, smaller either crop transport robots, harvest aids, or the robotic harvesting companies.
So do you have any comments on that, Inez?
So my experience is that big companies are booting small startup, and about the cost. So if you again pick the different technologies we saw before, let's say the hardware, the irons, the motors, the engines by itself are not expensive. So what makes everything really expensive is that right now we patch different technologies in a very not industrialized way, and this make the cost of the whole machines quite high. But if you are able again to go in high numbers, having accepted the technologies and everything can be really industrialized, what makes the machine successful or not is the artificial intelligence that is on board. And that artificial intelligence will be actually, there is a big cost at the beginning, but then at the end, everything is spread all over the world. It will be cost affordable, definitely. So again, the fact that the machines are very expensive is because now everything is developed at small scale and maybe not with a big industrial player really involved. They bought small company, they stay there to observe how the technologies grow. They are ready, but not really pretty involved, really involved.
So I got two comments on that. And that's one, we had a company here that has a picking platform that also has a transfer system, like a vacuum system. So basically the only thing that's not automized is the picking itself. And that company has really suffered from supply chain issues. And we've heard this from others, but this is an example that we have. So they had basically a better solution, but they have not been able to keep up with production because they just couldn't get all the pieces fast enough. On the other hand, we've really been trying to encourage folks to use off-the-shelf material to start with and to do like a plug-and-play system and to not develop every single thing themselves. We've had a lot of companies initially doing their own vision system, doing their own bin filler, doing their own all kinds of things, instead of using things that are already on the market, which will shorten those time frames. So those are two things that we have learned and that might work well. In terms of big companies jumping in, yeah, I agree, Lorenzo. It's been hard to get the bigger players to play, but I think they're getting ready to jump in. I think they were just not willing to invest themselves. But I think what I predict is some of the smaller companies some of the technology will be bought up by the big players when it's a little bit more obvious which ones are the winners. And then related to the to those little devices that go in the field by itself, I think there's lots of solutions out there now also in other fields. There's another sprayer company from New Zealand that has actually a feeder system. So, because one of the things with the autonomous sprayer is nice, but you still got to go out and fill it back up with water. What if you have something that comes and brings you the water and the mixture as you need? And that's one of the solutions. It's the same principle then with the grapes going and have something in and out. So I think there's a lot of different things that are coming on the market, which will sort out, which will advance the technology fast.
All right, thanks. So we have a question about stone fruit. Nobody's talked about stone fruit. I think those are maybe a little more difficult, especially peach and nectarine. Anybody want to make a comment about those?
Well, there is in California, there is a grower working with a company from Israel that uses a drone system to detach fruit, and so there is some work done on stone fruit. But the problem is that most of the trees are not there. Yeah, they're just bigger trees and harder to reach. So, but having, for example, something that can go to the fruit makes more sense. So there is some activity in stone fruit, but it's not as advanced as in other crops.
Right. That's what I thought.
Yeah,
So
I
you mean-
just adding
ahead.
to that, I agree that there is one company from Israel using flying drones, multiple drones to actually go and pick from larger trees. And that is a nice approach, a nice idea, because the drones give you a lot of mobility and you can access the bigger trees, the fruits on the bigger trees. However, the challenge there is the picking cycle, because it takes a drone quite a few seconds, tens of seconds to pick one fruit, and even deploying 4 or 6 of those drones, if you do the math, it's going to be very difficult to scale so that you have enough picking speed for the whole system to pick from those large trees. So although the approach is valid, still, if we can make those trees more geometrical, more compact, that would be a better solution than trying to pick from very large or unstructured trees.
Right. So, and as you mentioned, genetics and breeding for specific varieties that would be more amenable. But if we're waiting, for breeding, it takes on average 15 to 20 years to breed a new cultivar in any of the tree crops, I think. And that's quite fast if you really look at all of the things. So we're looking at quite a bit of time between now and the perfect solution, it sounds to me. And I have sort of a question I'd like all of you to kind of take a stab at. And that is, in terms of a fully robotic harvester, what do you think the time frame is for apples? Let's just say apples, since that's the one that's most. What's the time frame before we see that as the primary system for harvesting apples? Anybody want to take a stab? Come on, Stavros.
Well, first of all, I might argue that strawberries are closer, because we already have at least one company, which is actually local in Davis, that has machines that harvest strawberries in farms, and they're quite successful, still facing challenges. There is also a company from Florida. They have a pretty mature machine that also does packing on the machine, and they pick. So those are close. Now, whether they stay afloat, they have enough money to continue operations, and whether they grow, I don't know, but they're already doing it, and I think it's going to be gradual improvements. In the space of apples, if I'm not wrong, we don't have companies that are actually picking a lot of apples commercially by renting or deploying machines. There are a few prototypes, at least 2 companies I can think of, that have products out there that can pick. Maybe Ness knows more about one of them but both of them, because they're both picking in Washington State. So maybe she has more information on the performance on those machines. But I would think it's a few years before those apple picking machines can actually pick commercially. I don't know how many years. It's not going to be one or two, if you ask me. It's going to be more.
So I will also not give you a number, although I can tell you two things that that might play in our favor. First of all, we're really happy with the speed of development. It has really picked up. It has actually accelerated. Just within 1 year, just to basically frame this, just within 1 year, we've had huge improvement. Beforehand, we had consecutive hours that machines could pick. Last year, we already went to multiple days. Beforehand, we had a couple of bins. This is our picking containers that we were able to pick. Last year, hundreds of bins were picked. And the only real problem right now is actually the speed. So far, with 1 bin per hour or less, which is still below what hand picking would be. But we are expecting the same kind of exponential increase in all of these parameters this year. So after this year, the story will really reveal itself on how fast things can move. We are really looking forward to this. What unfortunately might play in our favor is also that we are expecting a big crop this year. So last year with a small crop, we already had problems picking it. If we have a big crop this year, we might have a real problem picking it, which might elevate the problem. And then also, I mean, we have ever rising every year. We have especially in Washington State, we have really high minimum wage and really high costs. The costs are rising. So basically every year the cost of the machine becomes more favorable in favor of being economically viable. So all of those things are at play. So I think this year is a very crucial year to have a lot of these things sort itself out. What I'm still missing a little bit, not in this discussion, but in general, is this the urgency more on a national level, more on a food security type of level. What we're talking about here is perennial crops. It's not so easy to replace them. And right now at the speed it's going, as a lot of these crops, they cannot be grown in certain countries anymore if we are not solving the problem of picking. But yet we have basically the public opinion being that that we're literally taking away jobs from people, and not the realization on the side of the politics that maybe it's important, maybe it is important for each country to have their own food supply and have it secured. And if you take a perennial tree out, you have for 10 years you got nothing, and that's those kinds of questions there. I think not for us to answer, but I think they play into this, and it's going to be very interesting to see how that plays out and how different countries handle it. I mean, but those are some of the larger questions. I think that we'll see. I don't think there's any answers there yet, and there's, I think, not public awareness, and it's really hard for us to raise that.
Yeah, that the political part of replacing workers is a political issue, but it's a big issue. You might want to take a look at, I don't know exactly how it ended, but we had a very similar issue in California back in the 70s with the tomato harvester. So we had we mechanized tomato harvesting from hand labor to mechanical labor harvesting. Developed. It's not so unsimilar as what you're predicting or proposing for fruit, and that is we had at UC Davis, we had a breeding program that focused on breeding tomatoes that could be harvested, and that was very successful. And that was teamed up with a group in Stavros's department that developed a tomato harvester. And so now in California, virtually all the tomatoes that are used for processing are harvested by machine. But we had in the 80s a lawsuit brought against the university for developing that technology and so on. And it went on for several years. I think in the end, it was settled without the university having to pay a whole lot. But we did go through, I just bring it up because we did go through that whole same scenario. A lot of people, and that was in the era of the very strong farm worker movement. And we did go through that era in California, and we're definitely on the other side of it now. All of our tomatoes are mechanically harvested that are for processing. So
I'd like to say one thing on the strawberry to your earlier question of how close are we to adoption. It is true that we have robotic harvesters in the strawberry fields right now, or probably as we speak, right? But it's also true that those are only at the present moment really only viable in the early season, right? There are no robotic harvesters that are successfully and profitably harvesting over the course of the year, right? At the beginning of the year when the plants are small and there's not so much foliage, it's easier to identify the fruit. They're feeling okay. But I'll point out that that's also the time of the year when growers have enough labor. When the growers are really pressed on labor is the peak production periods, and they need to supplement their crews. That's unfortunately the time of the year where the robots have the hardest time. And so I'm not sure that, at least the way the question was claimed, when will it be the primary harvest solution, the way that it has become for tomatoes? I don't see that happening in strawberries in the foreseeable future myself.
Thanks, Tim.
I would add that this seems to be the case. The possibility is that maybe those harvesters pick 30% of the crop during high season, or 40, I don't know, and then the rest is cleaned up or picked by humans. But of course, that combination has its own problems and challenges. I think the same will be true for apples. Some orchards will be harvested very efficiently. Again, if the fruits are very visible and well reachable. But if you start looking at averages over many orchards, that may not be the case. I don't know what even the efficiency will be. Maybe Ines have some numbers even now. You mentioned that speed needs to be improved. Yes, but what about efficiency? On average, do they pick 90% or do they pick 70%? And even if it's 70, then what happens to the rest of the fruit will still need people, right?
Yeah, so the best in a system that's really nicely suited, it's 90%, but we gave the companies 60 to 70% as a goal because we think that is more realistic, and because it also takes time to go to the difficult to reach fruit. So we feel like it's better to do the speed to get what you can get, and then we'll figure out the rest afterwards.
Even in blueberries right now, which are mechanically harvested, not robotics, but mechanically harvested, we lose 30% of blueberries during harvest, and it's viable. The labor is so expensive that we're willing to give up some of that fruit, and it's an uncomfortable story, right? Nobody likes admitting that 30% of the fruit doesn't make it out of the field, but it's the truth, and it's the truth in strawberries as well. We can't act like human pickers are seeing every individual berry. I think the rates of fruit left in the field are, it's based on some of the data that we've collected, around 25 or 30% as well.
Can I say something? We talk about labor costs, but this is highly variable depending on the area. It's different in Europe, different in Greece, different in Italy, different in the United States. Can we have an idea about California?
Or Washington.
And Washington as well, about the labor cost?
Yeah, our minimum wage is $15.74, but realistically, we have to pay close to $18 an hour per person, because we have to account for the cost of H2A, and that there's a prevailing wage rate.
Okay,
Yeah, and then with all of the other things added on, insurance sorts of things, we're around $19-20, I think.
okay.
Can I add something, Ted, about this aspect? So to me, of course, what's the main problem? That we have harvesting season just once per year. So we have just one shot where to test possible developments, improvement in technologies, and then we have to wait 1 year again to test additional improvements. So what could be really a big improvement in shortening a lot the time to market, to me, is also trying to develop a very sophisticated, realistic simulation model of the plant, of the orchard, so that you can start developing technology and testing technologies in very realistic settings, not only once per year, but actually all over the year, having some virtual model and what they typically call the digital twin, and that helps in developing the technology again all over the year, not just one per year, once per year. And that is at university level. Here in Bologna, we are making a lot of research in this direction, how to create something that is really realistic, also in terms of physics, not only in terms of appearance, but in terms of physics, on which we can test improvements, solutions, as we were in field, but indeed on a computer. That could be really a step change in making the time to market a bit shorter. And the other consideration that I would like to do is that early adopters will be crucial, because we cannot wait to have the supercomputer having high efficiency, very low cycle time, to say that the challenge is won. So actually we have to accept very maybe low performance robots and learn on field and improve step by step on field with the help of the farmers and of the growers and of the computers. Again, simulation will be crucial.
Thanks, Lorenzo. I think Stavros is going to disagree with you a lot about the computer simulations, right, Stavros?
Well, partially. I mean, there are, in terms of the perception system, the cameras and the computer vision, there is already a lot of work, yes, on creating artificial renderings, images of trees and fruits and foliage, and then creating training data for computer algorithms to learn and identify the fruits, etc. So this is a very promising approach, and it's already it's bearing fruit, if you will, already. But in terms of the physical interaction, this is extremely difficult, because anytime you physically interact, touch, push, break, squeeze things, it's very difficult, first of all, to model mathematically, but it's also very difficult to find all those parameters, the physical parameters in your model that reflect reality. Anywhere from modeling how the peach would bruise if you touched it harder or softer with a mechanical gripper with certain properties, to how would the branch react if you pushed it, what are the mechanical properties of the branch, etc. So it's a double challenge. One is creating a very realistic simulation environment in terms of the physics, like you mentioned, but the other challenge is populating that environment with the correct physical and physiological, perhaps, parameters to make it really realistic. So it's a noble cause. I think, you know, it's a research topic, but I find it very challenging to mature enough to give us results soon. And so that's why we see a lot of these companies and even labs eventually having to go to the fields, to the orchards over and over again. And if they have the cash, then go to the southern hemisphere so they double the time they can test actually there in the field.
So Lorenzo, just to let you know, I sort of I sort of set up Stavros because he spent a lot of time doing developing virtual trees. So anyway, we're getting near the end of the time that's allotted for this. So George, you want to take this
Yeah.
over?
Oh.
And is Francois still here?
Yes, yes, but I would like Ted before. I was lucky enough to attend Ines' talk in Angers last August. And Ines, I was wondering if you can share with us 2 or 3 provocative slides from your presentation about the robotic harvesting and some economics, as we discussed before the beginning of this meeting.
Yeah, sure, we can. Yeah, I'll do it. All right. Give me a sec here. It's going. Okay, so this is basically in relation to this picking robot. It is not in existence anymore. That was the first one that we tested on apples. It was a vacuum system, and we did a lot of the things that you guys discussed. But really, the simplest explanation of this was they ran out of money. They couldn't cycle it fast enough. They had investments of 20 million, but that was not enough at the time, because the investors really expected sales and harvest ready machines in 3 to 5 years, and that was just not possible. They did do 2 cycles per year in washing and New Zealand, but it took them already 2 years to just harvest fruit, and then they had to deal with the doubles, and they were never able to avoid damage and reach enough fruit. The machine kept on falling down, and and the speed was just never there, and it was just really heartbreaking to see that they were not able to make it. And we have several other people that are in that same boat right now. At some point in time. So we really, I think one of the things that scientists can do, a lot of scientists are here, is to basically try and really develop things that are open source so companies can actually take it, and it's faster for them to integrate little pieces that they can use and enable the companies to be in orchards and make it and really have growers integrated from the beginning. That really helps cycling faster and helps companies potentially get out on the other side and have machines to adopt. I think that's what I would say.
Thank you, Ines. And I would like to give the floor to Francois Lorenz, the ICHS president, for closing this episode.
Thank you very much, George, and Ted for the organizing this very nice art forum. I don't have much to say. I'm not a specialist on that, and I really enjoy all the presentation of Stavros and all the discussion, very rich. Actually, it's what we really want to have this exchange and even controversial discussion sometimes. I like your last slide, Ines. Actually, I couldn't attend your presentation, but it's really interesting. What I just keep in mind after many things, but after this given presentation is the importance of having a multidisciplinary approach in this kind of things, merging breeding, agronomy, and also socioeconomy. I like also your last point, Ines, to think about our research link with industry, and I think the open source system should be a very important thing to develop. And anyway, it's sort of thing we would like to develop within ISHS to have, and actually it's one of our strengths to have these different disciplines working together, and so it's also we would like to do. Just one point on breeding, and I just want to jump on what Ted said. I'm still a breeder and geneticist. It's not only a matter of length of cycle of selection. It's also more trait you want to add and more difficult or impossible it is to get. So in Apple, for example, to have there's no ideal fruit, but if you add new traits, it's completely impossible. So don't expect too much from breeding, and perhaps more on the culture system or things like that. And so everything is complex, but it's good that everybody is doing his own stuff. So thank you very, very much. And thanks to George and Ted again. And have a good day, night, whatever. Thank you.
All right, thanks, Francois. I just want to add a point that we hope to have the next Hort Forum actually address breeding, molecular biology, and molecular markers sorts of things. So we're putting that together now. It'll be a little while before we have another one, but just let anybody who's still on know that.
Don't expect
So
too much
thank you
from
again
the-
very much.
Don't expect too much from the markers in breeding, but it's for the next time.
Well, I think that'll be a little bit controversial too, so that'll be good.
Yeah, that's good.
Okay, thanks
Thank you very
everyone.
much. Thank you very much. Bye-bye.
Thank you. Bye-bye.
Bye.